So today we're going to be looking at weight and motion due to gravity. So let's consider gravity as a whole. So here we have the Earth and we have Jupiter. So pretty obviously, an object falls under gravity, and when it does, it accelerates. So say if you just released a ball, the ball would drop. Once it's released, it starts off with zero velocity, but the gravitational pull of the Earth causes it to accelerate, and the velocity of that ball will increase. If you were to drop a ball on Earth, the acceleration due to gravity would be the acceleration due to gravity is what we call g, would be 9.8 meters per second squared. Now, for practical calculation purposes, we will just round this up to 10. Now, if you were to drop that ball on Jupiter, the acceleration would be 24.79 meters per second squared, because the gravitational pull of an object is dependent upon its mass. Therefore, you will weigh more on Jupiter and less on Earth, because the weight of something is the force of a mass caused by the gravitational pull. So your weight, weight is mass times, an object's mass times g for Earth, that gravitational force, that gravitational pull. Something interesting about this, if you were to take, let's draw here, this is the Earth. So say you had a bowling ball, and say you had a feather. And you release them both. Now, if you could remove air resistance, both would hit the ground in the same time, because the acceleration does not depend on mass. So it doesn't matter if it's a bowling ball or a feather, they would both hit the ground in the same time. Now, if you were to do this, you would see the feather would hit the ground later, but that is nothing to do with the mass of that feather. It is everything to do with the air resistance pushing back on the feather. Now, when Commander David Scott was on the moon in the Apollo 15 mission, he actually demonstrated this experiment that Galileo had first spoken about in the 1600s. And there's actually, you can go to Google, there's footage of it where they dropped two objects, one with a higher mass than the other, and they both hit the ground of the moon at exactly the same time. And it works on the moon because you don't have air resistance. There's also a really nice video that was done by the BBC in the world's biggest vacuum chamber, where they actually took a bowling ball and a lovely feather, and they, in this vacuum chamber, released them, and they hit the ground at exactly the same time. In the history of science, it's said that Galileo dropped two balls of differing masses from the top of the Leaning Tower of Pisa. This may not have happened, this may have been a thought experiment, but if it had happened, they would have hit the ground at the same time. So let us look at some questions with considering gravity. So let's consider a ball of mass 0.2 kilograms, and it's thrown vertically upwards out of a window 4 meters above the ground. The ball is released with speed 8 meters per second. There is constant air resistance of 0.1 newtons in the direction of motion. How long until the ball hits the ground? Okay, so what we need to do is we need to draw a diagram with all the different forces acting on the ball. So we're going to say the ball starts here. This is the windowsill, and here's our ball, and this is on way up, so it's thrown up into the air, and we need to define up. We need to define firstly the direction of motion. So we're going, what way is going to be positive? So up is going to be positive, and we go up with some acceleratory force. Now the ball has mass 0.2 g newtons coming pulling it down. So this is the weight of the ball coming down, but it's also got air resistance. So 0.1 newtons is also pulling against the ball's motion going up. So let's think about what is the force acting on the ball. So the force is mass times acceleration. So the forces acting on the ball are, and this is in the negative direction, minus 0.2 g coming down the way, and there's also minus 0.1. Now the mass of the ball is 0.2, and there's some accelerating force on it that we don't know. So we can now work out that the acceleration for this ball will be minus 10.5 meters per second squared. Now, the initial velocity in this direction, u, is going to be 8 meters per second. So we're going to use v equals u plus at to calculate the time the ball takes to go up, and then it will go up, then it'll hit a point where it's going to slow down as it goes up, and then it's going to stop and then momentarily and then start falling back down. So where this velocity is 0. So the final velocity is going to be 0. Then we've got the initial velocity of 8, and we've got negative acceleration 10.5, and then some time t. So if we rearrange all of that, t1, so the first part of this motion is going to be 0.8762 seconds. Okay, now we need to find how far does the ball travel up. So we're going to use v squared equals u squared plus 2as. So we know that the final velocity is 0, then it's 8 squared plus 2 times minus 10.5 times s. Rearranging all of that, the distance it goes up before it starts to drop is going to be 3.05 meters. Now, we're now going to think about going down. So, on way down. So if we start, this is where it started, the ball started off. So the ball comes down, it's going to fall from up this height. This height here is 3.05 meters, and the window is 4 meters off the ground. Now, pulling the ball down, you've got 0.2 g newtons, but acting against the motion, you're going to have 0.1 newtons. And coming down, gravity is acting down upon this ball. So we need to find what is the force on the ball now, the acceleration of the ball now. So F equals ma. So we've got 0.2 g coming down, and minus, so this is going to be, because this is in the opposite direction, minus 0.1 equals the mass, which is 0.28. Now g, remember from previously, I'll just write this here because I never made that clear earlier, g is going to be 10. Okay, so that's the acceleration due to gravity. And if we slot everything in, you're going to have the acceleration is 9.5 meters per second squared. Okay, so now we need to think, we need time. So we're going to do, I'll be working here, we're going to use S equals U t plus a half a t squared. Now, at the top here, u equals 0. Now the distance is going to be this distance, add this distance. So you're going to have 3.05 plus 4 is equal to 0t plus a half 9.5 t squared. And we'll go with t2 just so that we know this is the second half of the motion. Rearranging all of that, we will get t2 is equal to 1.22 seconds. So from the top here down to the ground, 1.22 seconds. So the total time will be the time that it took from throwing it out of the window up this time, 0.762 plus the time from the highest point of its motion down to the ground again, plus 1.22, and that will be 1.98 seconds. let's look at another question. Okay, we're going to look at another question. So, a ball is dropped from a height of 30 meters above the ground. 2 seconds later, another ball is thrown upwards from the ground. With a speed of 5 meters per second. They collide at time t seconds after the first ball was dropped. Find t. Now, one of the hardest things with this is keeping a tab on what you are defining and what is happening. So let's draw our diagram. So you've got your first ball and it's dropped from a height of 30 meters. Okay, now it's got mass, some unknown mass, and it's going to be falling with a force of m1 g newtons. We're going to have the motion, again define the direction of motion, so we're going to have this as the direction of positive motion. Okay, so for the ball, it's accelerating down with an acceleration, and it's going to be minus g, because although it's going to be accelerating, that is the opposite direction to the motion that we've defined. Okay, so, and after some time t, it's going to collide with this ball. So this we have this ball that is released with an initial velocity of 5 meters per second, and it's released at some time t1 plus 2 seconds later. I won't put it down there just now. And it's going to be accelerating with, this is going to be decelerating. So that this is going to experience a as minus g as well in the opposite direction. So let's deal with the first ball. Ball 1. Okay. So we're going to be using S equals ut plus a half a t squared to consider the time. So we've got, this is going to be 0, this is going to be distance 1. This is the distance it travels. So S1, I'll just write that, is the distance I'm going to write ball 1 in here, okay, just so we know. Ball 1 travels before the collision. I just want to make that clear. T1, I'm just going to call it T because the time is the time before the collision, plus a half times minus 10 times t squared. Okay, so that will be minus 5 t squared. Now, the height, h, is going to be the height at which the collision occurs. Okay, so we know that h will be 30 minus 5 t squared. Because the ball's been released at 30 meters, and then it travels down some distance, 5t squared. Okay, so the height at which this collision occurs will be this. Now, let's now think about ball 2. So the initial speed is 5. So we have S equals U, and I'm putting 2 because we're dealing with ball 2. T2 plus a half a T2 squared. So the height that the ball travels is, the ball goes up, but after this height it collides with ball 1. So we're just going to put, instead of S2, we're going to put H. And it's going to be 5t2 plus a half minus 10 t squared d, and 2. Now, let's think about it. The time that T2 travels, T2 was released, the ball 2 was released 2 seconds after the first ball was released. So T2 can be thought of as T, the time that the first ball travels, minus 2, because it's 2 seconds behind. Its motion is 2 seconds behind. So we're going to substitute that in. It's going to be 5t minus 2. Wait a minute. I'm going to put this as a minus, because this will be minus 5. Minus 5, and it'll be t minus 2 squared. So we're going to work out what t minus 2 squared will be here, just so we can keep track of everything. So it's going to be t squared minus 4t plus 4, and then so we'll open these brackets out. It's going to be 5t minus 10, a better t, you can see it's actually a t, then minus, we're doing with this over here, so it's going to be minus 5t squared, minus 5 times 4, minus 4 is going to be plus 20t, minus 5 times plus 4 is going to be minus 20. Now let's collect things, but also let's take this and substitute it for this h. This is h. We can substitute this over here, so it's 30 minus 5t squared. Now look here, it's all t's, and we've only got one unknown. So we're going to gather things together. Gather like terms. So we're going to end up doing all that. You will get 60 is same as equals 25t. Therefore t is 2.4 seconds. Now we can use this to find, find the height of the collision. So we're just going to take this h equals 30 minus 5t squared, substitute for the time that we've got here, calculate it out, and you'll find it's 1.2 meters is when the collision takes place. So I hope that helps. With these ones, take your time. Be careful about signage. Define what direction motion is in. Be careful to define what symbols you're going to use for what. For example, knowing what times you're dealing with at which points, what distances you're dealing with, so you don't use the same symbol twice. All these things are things to be really aware of, because there's so many different elements to a question like this that you can easily get yourself tripped up. So I hope that helps.